Hi, today I'll be discussing compound B12 as a novel ACT-ROC inhibitor developed for the treatment of neuroblastoma. So here's the compound B12 drawn on ChemDraw, and this is a new ACT-ROC inhibitor that has been developed for the treatment of neuroblastoma, which is a challenging pediatric cancer. Compound B12 represents a promising approach in the treatment of this cancer, leveraging its dual inhibition of ACT and ROC pathways to induce differentiation and suppress tumour growth. Here's the article referenced in RSC format, and here's the IUPAC. So in terms of retrosynthetic aspect, 2 out of the 3 mechanisms were shown in the final compound. This carbon-carbon bond was formed initially by Suzuki coupling to obtain the pyrazole ring, then nucleophilic cyclization. This carbon-bromine bond was formed through bromination. Here are the 3 mechanisms I'll be discussing today. The first one is the Suzuki coupling catalytic cycle, and here's the overall reaction. So the palladium catalyst used is shown here. And this is a 14 electron coordinatively unsaturated with an oxidation state of 0, so it can participate in the catalytic cycle. The first step is an oxidative addition of the organohalide, so in this case organobromide, and the carbon-bromine bond will break. Now a carbon-palladium-bromine bond is formed where the oxidation state of the palladium increases by 2. In the presence of an oxygen-centered base, in this case being sodium hydrogen carbonate, in the presence of water it forms a hydroxide ion to be exchanged with the bromine. This hydroxide assists with a slow transmetallation step where now both organic compounds are attached to the palladium. The final step is reductive elimination to combine the 2 organic groups, where a new carbon-carbon bond is formed, and it reduces the palladium from palladium 2 to palladium 0. So the next reaction is bromination, and this was via electrophilic aromatic substitution, and here's the overall reaction. So the first step is the bromine donating electrons to the aluminium of the Lewis acid, and a bromine-aluminium bond is formed where the bromine is positively charged and the aluminium is negatively charged due to it accepting electrons. Here's the resonance shown, and this bromine is a pretty good electrophile. So to actually remove the positive charge on the bromine, the nucleophile will donate electrons to the bromine, breaking the bromine-bromine bond and forming a stable carbocation intermediate. To remove the hydrogen, this will essentially act as a base where it will deprotonate the compound, removing the hydrogen and forming the double bond to get your final product. So in terms of stereochemistry, the product retained the same stereochemistry as the final material, and therefore no stereogenic centers were created. And in terms of regioselectivity, due to resonance, the electron withdrawing groups are meta-directing, so they will direct the electrophile to carbon 3. So the final mechanism is nucleophilic aromatic substitution, and here's the overall reaction. The first step is the deprotonation of the nucleophile, and the lone pairs on the nucleophile will attack the carbon that's bonded to the leaving group, and this will essentially push out the pi electrons towards the ester. This is a rate determining step where the aromaticity is disrupted. In terms of your intermediate, the electron withdrawing group of the ester will help stabilize the negative charge, restoring aromaticity and removing the leaving group. As you can see here, the electrons are pushed around where it removes the chlorine to get your final product. So in terms of regioselectivity, the position of the substituents here is controlled by the leaving group. So essentially the substituent will just replace the leaving group. However, having an electron withdrawing group present will stabilize the intermediate as mentioned, and will also increase the rate of reaction. Thank you for watching.